Hello, welcome to our final project video for additive manufacturing and prosthetic design. For this project, we were tasked with designing a prosthesis for a right transtibial amputee. The constraints were that the prosthetic foot fit into a sandal, be able to attach to a proximal foot adapter, be made out of PLA, ABS, or some flexible filament such as NinjaFlex, and be 3D printable using FDM-based 3D printers. So this is a picture of our very first CAD design. We took initial measurements of the sandal and tried to create a generic foot design to fit inside of it. From the side view, you can see that the forefoot descends farther than the heel. This is due to the design of the sandal, which has a raised heel. In order to fit the adapter, we create a cutout in the heel. At this point in the design, we were not taking into account gait phases and rocker effects. We printed the foot at 15% hexagonal infill. We noticed immediately the disparity between heel and toe depth as well as the length of the foot. Another issue with the foot was that the dimensions of the cutout were too small to fit the adapter. During smash testing, the foot was obliterated due primarily to its structurally weak heel. A photo of the defunct would-be prosthesis shows the heel sheared vertically along the plane parallel to the print bed. We knew that, in order to have a viable foot, we had to dramatically strengthen the heel and improve shock absorption.
For our second iteration, we adopted a modular design with separate heel and forefoot pieces. The two pieces connected by four 10mm steel bolts. These bolts increased the structural rigidity of the prosthesis and allowed it to better accommodate force applied during the loading response phase of the gait. The heel cutout was also widened to better accommodate the adapter. We increased the infill density to 20% and added a NinjaFlex insert on the bottom of the heel to improve shock absorption and allow for a heel rocker effect. So for the second smash test, the foot survived the smash test under normal conditions but failed when more force was applied. The design introduces an unwanted stress point in the forefoot, causing it to shear during the terminal stance phase of gait. It also did not fit into the sandal due to its bulkhead profile.
For the third iteration, we shrunk the size of the heel and altered the forefoot to make it more solid. The addition of a NinjaFlex insert under the toe and in between the two components provided for toe and ankle rocker effects. We also added a piece of NinjaFlex insert underneath the adapter to reduce shearing. The new foot was significantly more sturdy than previous iterations. It held up during testing despite considerable force being applied. During walk testing, the heel and forefoot held up very well to the large stresses applied during the loading response and terminal stance phases of the gait. The toe, heel, and ankle rocker effects were also noticeable to the tester. However, the foot had a tendency to pronate. This pronation was due to stresses in the adapter cutout. This design flaw could be remedied by increasing infill that region of the heel, or by introducing a flexible filament as a buffer between the adapter and the cutout walls. This is our final design. The size of the forefoot has been reduced to improve and fit in the sandal. The design can further be improved by reducing the diameter for the bolts as it has a safety factor that is too high for the prosthesis. Thank you for watching.